So we will get two examples. We will see in the next class. In the previous class there are two examples. One is, say, we are written the grammar like that. That means either n t p s, where n is nothing but s, t is nothing but ab, and we will see the productions rule. This is nothing but s a s b, and say this is from S we will get AB, that we will get. And the language that is generated by this grammar, what we will see, this is a to the power n b to the power n greater than equals to 1. And we will also see another example where we will see that the grammar is also, this is NTPS, and set of non-terminals, that is the start state, set of terminal ABC, and we will see some productions rule, that is S from ASA, or you can say S from BSB, and say S from C, that we will see. So the thing is that, and the language generated by this particular grammar, that is omega c, omega r, where omega is belongs to a b star, that we will see. That is these examples. What I am saying, these examples are slightly more restricted versions of CFG. This example, these examples, are of slightly more restricted. This is nothing but, we can say, slightly more restricted version, version of context free grammar. Because why? Because we see the productions rule. That means if we see the productions rule, if we see the production rules, you observe that the right side of the productions rule, right side of the production rules, along along with terminus, we have one non-terminal. We have one non-terminal itself. তার মানে এখানে তুমি ভালো করে দেখলে দেখতে পাবে আমরা এখানে এস থেকে এএসএ নিচ্ছি। তার মানে এই যে রাইট সাইড অফ দ্য প্রোডাকশন রুল, there is a terminal, this is a terminal, and as well as there is non-terminal. So what we will see, that right side of the production rule along with the terminals, we have one non-terminal, and so it is a restricted version. What I am saying, that it is a restricted version. It is a restricted version of CFG, because what I am saying, in CFG, that is under CFG, but it is slightly restricted versions of CFG, because what we know, that in CFG, if A is derives alpha, where A is a set of non-terminals and alpha can be set of V star, and what is V? V is terminal, non-terminal. That is the combination of that. So this is under CFG, but there is some more restricted versions of the CFG. They will name this particular grammar, that is called linear grammar. They will say this is called linear grammar, that is under CFG. But if the question asks what do you mean by linear grammar, then you can say that type of thing, that is also under CFG, but slightly restricted versions. Why restriction version? Because the right side will consist of as well as terminal, then non-terminal, then again terminal, like that. So that is slightly restricted versions of CFG, and that particular grammar is known as linear grammar. And the and the language and the languages languages generated generated by this grammar generated by this grammar, that is called linear languages. It's called linear languages. So in linear grammar, right side of the productions rule has at most one non-terminal. That is a restriction. That means, what is the restriction? That means, linear grammar in case of linear grammar, what we can say, that side of the production right side of the production rules, you know has at most one non-terminus one non-terminus. That is the thing. That means that should be CFG, but slightly restricted, and the restricted as versions means the right side of the productions rule that consists at most one non-terminal. That is the thing that you should remember. That is the concept of linear grammar. So linear grammar is not another form of Chomsky normal form, that is under CFG, but slightly restricted versions of CFG. And what is the restrictions they are imposing? The restrictions is right hand side of the productions rule that will consist at most one non-terminus. That is the thing we can say about that. So the thing is that, so now we will discuss, because we already discussed, I have to discuss the uh, type 3, or you know linear, that is the regular grammar, and we will see that how it will work like that. So the thing is that, let's see, type 3, that is regular, that means, type 3. So that can also be, that is the, linear grammar is has some restrictions, so what we can say, what we discussed, that is the, concept of linear grammar. It is not a type 3 grammar, because in type 3 the right hand side is a non-terminal that will be followed by, terminal that will be followed by a non-terminal. But in that particular example, the right side of the productions rules consist of a terminal that is followed by a non-terminal and then followed by a terminal. So it is not type 3 rather than higher versions of this. So it may be possible in some books you will find that it is type 3 type, but I am saying that it is, not, rather than, you can say, type 3 grammar. It is not rather than type 3 grammar, because what we find, because, in type 3 grammar, the right side the right side is a terminal that is followed, you know by a non-terminal, like that, from A to AB and A to B. We will find that where A and B, that is a set of non-terminals, small a is set of terminals, and B is also set of terminal union, etc. So like that. So but in this example, but in this, example, the right side of the productions, the right side of the production rules, consist of a terminal followed by you know followed by a non-terminal, followed by a non-terminal, then followed by a terminal, then again you know followed by a terminal. That means from S we are getting ASP, like that. That means terminal, then non-terminal, then again terminal. So it is not type T rather than higher version of this. So what we can say? So it is not type 3, you can say, rather than higher version of this. So we can say that is under type 2. So there in some books it can be described in a different way, but I think that should be the correct thing. So what we can say about the type 3, that means regular grammar. If we say type 3, that means that is regular grammar, and we already know the rule. That means either you can say from A we are deriving, say you know A B B, where this A and B that is belongs to non-terminal, and small b that belongs to terminal. That is the thing. Like that, if we say an example, a grammar is like that, say you know AB slash A, or from B we are generating AB or BB or A or B, like that. So this is the, you can say, an example of regular grammar. Or you can write, that means you can say that is a right regular grammar, because the variable is present in the right side of the productions. The variable is present in the right side of the productions. So you can say that is the right regular grammar. Or this another form you can write like that. If we write this is a B A B, like that, in that particular format, that means BAB, that means the non-terminal or variable that is present in the left side of the productions. So in that particular case, what we can say, that is A and B is belongs to N, and small and A is belongs to terminals. So you can say, you can name as left regular grammar, or you can say this is right regular grammar. You can write like that. So the thing is that, but both that cannot be possible. That means it should be as well as left regular grammar and right regular grammar. That cannot be. That means if the rule consists, say if rule consists like that, from A we are getting BAB, and from B we are getting ABA, like that, that is nothing but left regular grammar, and this is right regular grammar. What we can say, that both cannot be possible. That means if and cannot be possible, and if you will find that both rule, so that is not type 3. That is not type 3. That means if this both rule are present, then that should not be type 3. Now if the questions you can ask, that means which one is powerful. If we ask the questions that which one is powerful, that finite automata, that means this is the accepting device, or regular grammar, that is the generating device, which one is powerful. So if we search for that, so let's if we try to you know convert from finite automata to regular grammar. If we want to try to convert what we already know, that if this is a say automata, it will start it with a, and whatever be the thing, it can like that. So if we express it by using a grammar from a, after getting a we will reach b, so we can write simply ab, and in b, from if we get a that is remains in b, so we can write ab, and if b that is also remains in b, and since that is the final, we can say we are giving epsilon. So that is regular, we will get this right regular grammar, because you will see that variable b is present in the right side of the productions. So that is nothing but the language we will generate. That means the corresponding language, that is nothing but set of all strings, set of all strings, that is starting with a. So now if we try to convert it, say we are trying to convert this right regular grammar to left regular grammar. I am trying to convert the right regular grammar to left regular grammar. And now by reversing the grammar, we can say that the language what this right left regular grammar generated is same as the language generated by right regular grammar. What I am saying, that I am just converting. I am just converting. You are generating this right regular grammar, right? Now you are converting this grammar to the left regular grammar. Now the question is, if we convert it into left regular grammar, then the language that is generated by the left regular grammar, that will be same as the language generated by the right linear grammar. So what I am saying, now by reversing the grammar, can we say that the languages that the languages what that left regular grammar generated is same as languages you know generated by right regular grammar. That is the the questions that we arise. So that let's see what will happen. That means first we have to convert this. We are getting this right regular grammar. You have to convert it into left regular grammar. If we want to convert it, then what we can say, from this a we are converting it. That means here the variable will be present at the right side, so if I write that variable should be present in the left side, that okay. And from b, what we will get, say ba, bb, or epsilon. We are just converting the corresponding language. If we convert this particular language, say I am converting this, so yeah, of course, that is nothing but this is left regular grammar. That is a left regular grammar. Now, so the language that is generated by, that is a reverse of a language. That means what I am saying, in that particular grammar you are generating what is the language, the set of all strings starting with a. So if we just right linear grammar is changed to left linear grammar. So by this grammar, if we want to produce the language, then that will give you the language all strings that is end with a. Is it correct? That I am asking. That means that is A to BA, and you will say that we are replacing B every time. That means it always been happen that that will be end with A. So the thing is that what we will get, that means if this is a finite automata, the finite automata accepts some language, that is L. Now the thing is, this finite automata is converted into we are representing the right regular grammar, and the corresponding language is also L. What I am doing now, you are reversing it. You are reverse the grammar, and we will get left regular grammar. And what the language we receive, that is also reverse. The language that we receive, that is also reserved. So the thing is that that is the interesting phenomenon that we observe. What I am observing, a finite automata, if we convert it into right regular grammar, and if we reverse it, we will get left regular grammar, but as well as the language that is generated by this right regular grammar, that should also reverse, that is also reverse. So how to convert finite automata which gives you you know left regular grammar, because here from finite automata আমি কিন্তু সেই ফাইনাইট অটোমেটা থেকে কিন্তু আমি সেই লেফট রেগুলার গ্রামার জেনারেট করতে পারলাম না। কেন পারলাম না? কারণ ফাইনাইট অটোমেটা যদি এল ল্যাঙ্গুয়েজকে অ্যাকসেপ্ট করে, তাহলে আমার গ্রামারটা কিন্তু রিভার্স অফ এল কে জেনারেট করতে পারছে। তার মানে কি, আমি ফাইনাইট অটোমেটা থেকে আমি যদি রাইট আমার রেগুলার গ্রামার আছে এবং সেখান থেকে যদি আমি লেফট রেগুলার গ্রামার তৈরি করি, তাহলে কিন্তু ল্যাঙ্গুয়েজটা রিভার্স হয়ে যাচ্ছে, মানে এই ল্যাঙ্গুয়েজটা কিন্তু এই ফাইনাইট অটোমেটা আর অ্যাকসেপ্ট করবে না। তাহলে আমাকে ভাবতে হবে যে কি করে আমি কনভার্ট করতে পারি। তার মানে হাউ টু কনভার্ট this particular finite automata which give this left regular grammar. So what we can say, that first we have to design a finite automata, say which is accepting and language L. First we have to reverse it. We have to reverse this finite automata. So if we reverse, we will also get a finite automata, but that will accept the language which is reverse. Now we are designing the right regular grammar for that. So this right regular grammar will accept the reverse language, and then what we get, we again do the reversing of that. So if we do reversing of that, we will get ref regular grammar, and the language that is produced is nothing but the reverse of that, and we will get L. So of course this procedure is not straightforward, but we can produce like that. So that is the one of the way to produce that. So the thing is that, so we are producing this. I think it makes sense that that is not a straightforward. We are getting a finite automata like that. What I am saying, that you have to say a finite automata. Say this is the corresponding say finite automata. Now what will happen? First step, you have to just reverse the finite automata. You know how to reverse, and you just changing the arrow, and initial and final state will be changing. So this initial state will be final change. You are just reversing the arrow, and that becomes the final will be initial, and this is like that. This is like that. This is a comma b. I'm writing a comma b. So that is the reverse. So if we now write the corresponding right regular grammar for that, because the finite automata is reverse. That means language is also reverse. That means that is ending with a uh, you know uh, ending with starting with a, and that will be ending with a. That is the difference between that. And if we write regular grammar for that, we will find that b, from b, if we get a, we are reaching b. From b is again b, and if we get a, we will reach a. So a to a, and that is the corresponding. And this particular grammar, this grammar gives complement reverse of this language. That means this is nothing but what we will get. That is nothing but starting with a, and that is nothing but ending with a. So the thing is that in that particular case, what we can see that uh, uh, so this will give you the value L. So what we can say now again, if we reversing the productions, that means because we are getting this RRR, now we are reversing the productions. If we reversing the productions, what we will get from B, this is BA, BB, AA, and from A to epsilon. That means this particular left regular grammar, which which is that will give you the language L. So for finite automata, we get a regular grammar, and that is, I think, okay. So what we will get? So for finite automata, what we get? We get regular grammar. Now we will see that whether we can generate finite automata or not. That means now what we can see now, see that for regular grammar, whether we can generate finite automata or not. That is the case that we should think of that whether for regular grammar, whether we can generate the finite automata or not. So say the right regular grammar is written like that. From A, this is AB or BA or B. From B, from A to C, B to B, and from C, A to A, B to C, A. That is the thing. So that means uh, you know uh, that means what I am saying, that means A on B, going to A, going to A, and end with B. আমি তো এটা থেকে বুঝতে পারি এটার মানে কি, যে এর উপর বি পড়লো, ধরো এই যে এর উপর বি পড়লো, এ পড়লো একই ব্যাপার, এর উপর আমি ধরে নিলাম বি পড়লো, that will going to A itself, and that will be ending with B. Or you can say from C on going to A, যখন স্মল a পড়েছে তখন সে a তে যাবে, and it will be ending with that particular a. And so from that what we can say, that a is the corresponding final state. A is the final state. We can see that a is the final state. So now what we can say about that, that is nothing but if we write this, that means A on B, that is going to A, and that will be ending with B. And so if we write like that, A, you know if we give B, that will be A, and that will be ending with B, that will be ending with B. And as well as if we consider B, so if we place A, that will be go to another state, say that is B. On B, if B will be given, that will be in B, and on A it will go to another state, that is C. Now the thing is, from C, if A is given small a, it will be back to A, right? And when B, that will be in C. And of course the C, that will be end with that will be end with A. So that's why I'm saying it is end with A. That means when it gives A, that will be ending. So that means we can say that A can be treated as a final state. So the thing is that if you know we are given a left regular grammar, if we are given a left regular grammar, say this grammar will generate the language L. If we reverse it, we will get the right regular grammar, which will generate the language which is reverse of that. Then we can design a finite automata, and this particular finite automata will accept the language that is same as R reverse. Now if we again reverse this, then we will get the finite automata, and that will accept the language L. That means what we will see, that if we a regular grammar, then we can convert it easily into finite automata, and if we have a finite automata, we can convert it into regular grammar. That means you can say that both are equivalent in power. That means in power of recognition of language or generative. That means both are equivalent in power. That we can show from that. So that is the one of the thing that we can you know we can see from that. Now the thing is that is you can say about the regular regular grammar. And the thing is that we know there is a that is the type 3 grammar, and about type 2. In the previous class we will see there are lots of example of context free context free grammar. And what we will see, that actually this is a particular context free grammar. That particular grammar generates language. That means this particular grammar will generate that language, that is called context free language. And this context free language is accepted by an automaton. This automaton is known as push down automaton. This is known as push down automaton. So the thing is that the context free grammar, this grammar generates language, the language name as context free language, and this context free language is accepted by automaton. This particular automaton is known as push down automaton. So the grammar is written like that. From A, that derives alpha, where A that belongs to set of, you can say non-terminals, and this alpha can belongs to terminal, non-terminals, union terminals, and the combination of that. So what we can write from that, that means whenever, whatever, whatever be a, whatever be a, we can replace, alpha on a without depending, without depend on the, without depend on the context, without depend on the context. That means whenever we get a, we are replacing it with alpha, so without depend on context, so it is called context free. So that's why it is called context free. So what we can say, you know from a, that is say a productions rule. So now what we will see, that means when a b is there, I can replace it, this a, with ab. There is a no problem. That is not depending on the context. But what do you mean by context? That means if the rule may be such that if this is a, then you can replace it with a. If the productions rule should be written like that, then what you can say, that means if we write a b, then depending on the context, that means whenever there is a, we are not replacing here, I have to see the previous letter. That means I have to see the context, and if the context will matches, then only we can replace it by that. So this is called context sensitive. If the rule is written like that, we will see it later. That is context sensitive language. That is context sensitive language. That is depend on the context. Okay. So the thing is that you should remember, that means if a grammar, if a grammar is regular grammar, then of course it must be CFG. Then it must be CFG. That means if this is a regular grammar, then it must be CFG. But the reverse is not true like that. So the thing is that you know uh, if we say there are lots of properties of the CFG, that means if we break the CFG into different parts, that means CFG can be break into two form like that. What I am saying, that left recursive, this is a left recursive, and the thing is that right recursive, that is actually the thing that you will be introduced when you dealing with compiler. Or CFG can be break into two parts, that is also important, that is ambiguous. Ambiguous, because what I am saying in the first class, in the previous class, that Noam Chomsky actually developed the concept of grammar, and he is a he is a scientist from the domain of linguistics. So the thing is that we are inherited the thing from linguistics. So that means the pros and cons of the computer system, that will be not taken care of. So that's why there is some ambiguities that is remain in the CFG, and that is called. So that's why there are two parts. One is the ambiguous, and another is ambiguous, unambiguous thing. And the CFG also can be uh, you know uh, break into two parts. That means deterministic CFG, and non-deterministic, and non-deterministic. And what we are saying, that the language that is accepted, the context free grammar generates the languages, and that particular languages accepted by PDA, and PDA has post down automata has two versions. One is deterministic PDA and one is non-deterministic PDA. So there are some languages which cannot be accepted by deterministic PDA, but that is CFG. That means the CFG has two parts. One set of CFG that can be accepted by deterministic. If it is accepted by deterministic, then obviously it is accepted by non-determinism. But the thing is that there are some language we can we will be seeing that that particular language can be accepted by non-deterministic PDA, but that cannot be accepted by deterministic PDA. And so there is a difference between this. So there are three parts. One is you know deterministic, that means the language, that means the CFG, which is accepted by deterministic PDA, that is deterministic CFG, and that are accepted by non-deterministic PDA. And of course you should remember that this non-deterministic PDA and deterministic PDA has not same power, like that what we see in the finite automaton, that non-deterministic finite automaton and deterministic finite automaton, that both accept the same set of language, and this set of language is called regular languages. That means you cannot generate any language, you cannot find any language which is accepted by you know deterministic finite automata and you know non-deterministic finite automata, that cannot be accepted by deterministic finite. There is no set, no language. That means if a language is accepted by deterministic finite state automata, the same language is also been accepted by non-deterministic finite automata. Though the non-deterministic finite state automata has more powerful in respect of, you always find if we convert a non-deterministic finite state automata into deterministic finite state automata, it may be possible that the number of states will be exponentially blow up. But you should remember the thing, that means you cannot find any language which is accepted by non-deterministic finite automata and cannot accepted by deterministic finite automata. So in terms of recognition of language, what we can say, that means deterministic finite state automata and non-deterministic finite state automata have same accepting capability. But that will not true for deterministic PDA and non-deterministic PDA, because there are some language you can find which is accepted by non-deterministic PDA, but that cannot be accepted by deterministic PDA. So that means non-deterministic PDA, that is the general versions, and if we put some restrictions, then that is nothing but deterministic PDA. But non-deterministic PDA accept, you can prove that there are some language which is accepted by non-deterministic PDA that cannot be accepted by deterministic PDA. So the thing is that we will see all those stuffs. So the thing is that some there are some properties of context free grammar. There are some properties of context free grammar. What we can say, that given a string, say we can say that given a string w, and say given a CFG, that means a string is given and as well as a grammar is given. Say given a CFG, and that that generate a language, now now does this particular string that belongs to the language? That is the question. That means we have a string, we have a CFG. Now the question is, that particular CFG will generate the language. Now whether this particular string will belong to the language, that is the question. So if you write an algorithm, that means what I am saying, that means that a grammar is given. What we find in case of CFG, what we can say, that say the the grammar, the first grammar that we take, and say the, I can write any grammar, a to the power n, b to the power n, if you can write this type of this particular grammar. So what we find, the productions rule is nothing but a s b, and from s to ab. This is the and the language that is generated, a to the power n, b to the power n is greater than equals to 1. Now the question is, if a string is given, say aa, that is w, that is a string. Now whether you can say that the given string, that particular string is belongs to this language, whether you can say or not, that is the question. So what should be your algorithm? Your algorithm may be like that: the set of all strings that are generated in one step by this grammar, because you have to you have only the grammar. So the thing is that what you have to say, that in one step, you generate uh, uh, the grammar. Say in one step I am generating, say s equals to ab. We are generating this particular string and check whether the string that is given, that will be matches with ab or not. And then set up all strings that are generated in two step. In two step means, from a to asb, and you can put the value, this string. So in two step, in only one string can be generated, whether this particular string will be belongs to this. So I have to check like that. That means if we write an just a brute force algorithm for that, the algorithm should be like that. If we say step 1, then set of all strings, that are generated, set of all strings that are generated in one step, and now check whether, check whether the string is in w or not. In the second step, what we can say, what I am writing in the second step, we have to find set of all strings that say are generated, in say two steps, and you have to check whether the string is in w or not. So the thing is that then it should goes on like that. So it goes to say, so it say goes to case steps. But if if this after case step we will find that particular string is not belongs to the language, then it continues, then it continues, and might go to infinite length, and might go to infinite, infinite length. So then you may fixed with finite length, but then we can say how much time your algorithm will run. So that's why you are fixing the algorithm. That means that will go up to length something 10 or 15, whatever you think. Then you may fixed, fixed finite length. That means after the string length, say if the string length is 15, then your algorithm will stop. But there is also problem. But say if either your production rule, if it contains a to epsilon or a to b, then the sentential from may not string. It may be possible because we are replacing from a to b, a to c. That means the thing is that if you are doing this particular rule 100 times, then it may be possible that your length will not grow to length 15, because you are replacing, you are increasing the length, and then you are substituting epsilon. That means that your length is shrink. Or otherwise you may replace this a is also non-terminal, this b is also non-terminal. That means you are replacing this non-terminal. That means within say 1 to 15 you are replacing this a to b say 100 times, then your length will not increasing, because you are replacing a with b 100 times. Then of course the string length will be not increasing. So that means that is also creating problem. If your productions rule will contain this type of productions, this is called unit production. This is called unit production. This type of productions rule is known as unit production. So if, কারণ তুমি ভালো করে দেখো, মানে অনেকটা এরকম রিয়েল নাম্বারের মতো। রিয়েল নাম্বার আমরা কি বলি, 1.1 থেকে 1.2 এর মধ্যে কতগুলো নাম্বার আছে, ইউ উইল সে ইনফাইনাইট, বিকজ 1.1 থেকে 1.2 এর মধ্যে লক্ষ লক্ষ নাম্বার থাকতে পারে 1.10000, 1.10001, 1.10 times 01. So that should be infinite number of points, maybe they are between 1.1 to between 1.2. That is the fallacy. So in that particular case also, ধরো তোমার একটা আমি বললাম তোমার অ্যালগরিদমটা যখন স্ট্রিং লেন্থটা 15 হবে তোমার অ্যালগরিদমটা স্টপ করে যাবে। তাহলে 15 হবে মানে কি, আমার ধরো এরকম একটা অ্যালগরিদম, ধরো এ এস এ এস এ বি আছে ধরো এরকম, এবং সেখান থেকে তুমি বলেছো এ থেকে ধরো আমি এ বি আছে, এবং আমার বক্তব্য এ থেকে এখানে একটা প্রোডাকশন বিও আছে, আবার আমি ধরলাম বি থেকে তোমার প্রোডাকশন এপসাইলন আছে। সো দ্য থিং ইজ দ্যাট ইউনো তার মানে আমার এখানে স্ট্রিং লেন্থটা যে বাড়ছে, এই স্ট্রিং লেন্থটা যে বাড়বে, তার মানে এটা তো আমি ধরো এ থেকে আমি বললাম এ এ বি হলো, এবং লেন্থ এ থেকে আবার এ এ এ বি আমি এরকম লেন্থগুলোকে বাড়াচ্ছি। আমি বলে দিলাম ঠিক আছে আমার এই লেন্থটা যখন 1 2 3 4 5 6 7 হবে তখন থেমে যাবে, তাহলে আমার প্রোগ্রামটা এখানে থেমে যাওয়ার কথা। কিন্তু এখানে যদি আবার ইউনিট প্রোডাকশনস বসে, মানে এ থেকে বি এলো, তাহলে দেখো লেন্থ কিন্তু বাড়ছে না। আবার যদি ঘটনাটা এরকম হয়, আবার বিটা যদি এপসাইলন হয়, তাহলে কিন্তু লেন্থটা আমার আর বাড়বে না। তার মানে আমার প্রোডাকশন রুলটা আমি অত ভালো করে লিখিনি, বাট ইট মে বি পসিবল দ্যাট এই এরকম ইউনিট প্রোডাকশন থাকার ফলে এর মধ্যেখানে স্টেপ, মানে অ্যাকচুয়ালি আমি দুটো স্টেপে এটা পেয়ে যাওয়ার কথা, কিন্তু মধ্যেখানে আমি ইউনিট প্রোডাকশনস এবং এপসাইলন প্রোডাকশনস থাকার জন্য হয়তো দেখা যাবে আমি সাবস্টিটিউট করেই যাচ্ছি, অথচ স্ট্রিং লেন্থটা বাড়ছে না। মানে হয়তো আমি লেন্থটা লেন্থ সিক্সের মধ্যেখানে আমার 6টা স্টেপে হয়ে যাওয়ার কথা, বাট অ্যাকচুয়ালি আমার লাগছে অনেক স্টেপ, মানে সেটা আমি জানি না, কাউন্ট করতে পারছি না, বিকজ দেয়ার ইজ এ epsilon productions and unit productions. So the thing is that, so what we can say, that means if this a equals to epsilon or a is belongs to b, that means unit productions, what we can say, then the sentential, that means then the sentential from may not shrink, may not shrink, may not shrink, and it is never be possible that when it stop, we don't know that when it stops. So that means we are building the thing, that means why we should need something, that means it would be better that if there we can remove the unit productions, it will be better if we can remove the null productions, and what are the reason behind that, we will think of that. So if a grammar does not contain epsilon, say, now the question may comes like that, if a grammar that does not contain epsilon production, epsilon production, or unit productions, if your grammar does not contain these productions, that means say this a2 epsilon or a2b, if this your grammar is not, so in worst case the grammar will be in, say, in worst case, I am saying in worst case, the entire grammar, the entire grammar, you can say, will be in this particular grammatical form, production rules are in that particular form, it may be possible. So if we do the derivations using this in derivations, in derivation process, in derivation process, either we increase string, what we can say, either in that particular case we increase string length by 1, That means a is either it is replaced by two variable, or it is replaced by only one terminal, one you know terminal variable. Either it will be length it increases by 2, either in the worst case it will be replaced by a terminal. So the number of strings, that means what we can say, if we want to generate something, say a to a, it will be better if we write in the form, say you know a production should say bc, and from b to small b, and this is capital C, and from capital C to small c. So what we can say, that from a we are getting bc, and then we are replacing b, and then we are replacing c. So if we want to generate the string length w, if 2, then actually what we can say, we are applying this rule, then again. So in the worst case it may be possible that if we want to generate the string length w, the string length 2, that means we have to substitute this 4 times, but it may be possible like that. Say from a to, if we write a, say, and if we say I am writing, either I have to write in that particular form. So it may be, say I am taking an example, it will be better. That means, just a minute, it will be in some different form. So it will be better if we take example, then it will be clear to you that what I am trying to say. That means if the grammar is written in that particular format, then what will happening, that is the thing. That means you know mm, what will be happening there. So if we write like that, that means I have to write the all the grammar is written in that particular format, say ad, say from d to sb, from s to ab, all are in format, and either a is a or b is b. So the thing is that uh, what we can say from s to ad, then in every step either that will be incremented, either it would be replaced by variable 2, or either you can say it would be replaced by terminal. So the thing is, from a, if we this is a and d is produced, and from a will be, say, a, in place of d we can again write, say, sb. Then that means that will be incremented by 1, and say again we can replace a with ab. So that means this a will be replaced by a, that means this a will be again replaced by this will be replaced by b, and this will be replaced by so that means if we get, this is the length 4, if we want to generate this length 4 terminal string, we are getting length 4 non-terminals, and then you are substituting it value 4 times, then you will get that. That means if the length is 4, we are substituting 4 times, and as well as we have to generate it by using 3 times. In worst case it may be possible we are generating the length of the string using 4 times. So maximum you can say That means to generate the length of the string 4, that means we have to substitute worst case. If we take the worst case, it will take the double of the size of the string, that I want to say. That means, so the number of steps, what I am saying in that particular case, in the derivation process, what we will see that either we increase the string length by 1, or in that particular case, this is a, the string length is either increased by 1 or it is replaced by one terminal, but the length will not change, the length will be same. So if we say there are number of steps, the number of steps that required to generate a string of length w using using such a grammar is, first what you have to do, if you want to, first the grammar is, you can say, first what you have to do, first you, if you want to increase the length of the string, say if you want to increase the length of the string from s to w, so in w steps, we need a w step, I can increase the string length to w. We are increasing the string length to w by replacing it in w step, and also you need, and in w step you are replacing with the terminal. So in w steps, what we can say, we can replace every variable with terminal. So in worst case, if we consider in worst case, so in worst case what we will get, it takes 2w steps in order to generate 2w steps in order to generate a string of length w, which does not contain epsilon, which of course does not contain epsilon, and unit productions, and unit production. So our algo is supposed to stop after 2 omega steps. So in that particular case, our algo is supposed to stop, because that is the worst case, after 2w steps. So now if we say about the complexity, if we say, if we want to find the corresponding complexity, what we can say, so if we consider the first step, you have to examine all p sentential from, all p sentential from, if w is present, otherwise in second step I will examine, otherwise, that means first step আমরা প্রথম p স্টেপে ধরলাম যে p সেন্টেন্সিয়াল ফর্ম থেকে স্ট্রিংগুলোকে জেনারেট করলাম, সেগুলো দেখলাম whether w is present or not, otherwise সেকেন্ড স্টেপে আমি কি করব, we have to examine p square sentential from. So in first productions, p PR replace all possible variable with terminals. So we get p square sentential form. এখন আমাকে কি করতে হবে, এই p square sentential form কে দেখতে হবে w এর সাথে ম্যাচ করে যে এটা ঠিকঠাক হচ্ছে কিনা। দেন আমাকে আবার p কিউব sentential form, তার মানে অ্যালগোটা টেক করবে কি p প্লাস p স্কয়ার প্লাস p কিউব, এবং এটা রান করবে কত p টু দি পাওয়ার 2w পর্যন্ত, 2w পর্যন্ত। তার মানে এর যদি কমপ্লেক্সিটি হয় ইটস নিয়ার অ্যাবাউট p to the power plus 1, that is the corresponding complexity, and of course that is nothing but it is exponential complexity. It is exponential complexity, and of course the exponential complexity is not a very good thing. So we try to do the same thing. That means whether a string belongs to the language or not, if the grammar is given, the grammar is in CFG form. So if we try to do the same thing in polynomial complexity, and that can be done by using an algorithm that is one of the important algorithm for competitive exam, that is CYK algorithm. And that is nothing but, that is also important in algorithm also, this is called membership. This is membership of any string, whether the string is belongs to the language or not. Any string you can find using the complexity, that is polynomial time complexity তে আমরা বার করতে পারি. This is called CYK algorithm. That is another algorithm, and it is a very interesting algorithm. যে অ্যালগরিদম দিয়ে এই এক্সপোনেনশিয়াল, এটা যে দেখলাম আমরা এক্সপোনেনশিয়াল টাইম কমপ্লেক্সিটি কি, এটা মেম্বারশিপ কথাটার অর্থ কি, যে whether this particular string is belongs to the language or not if a CFG is given to you. সো এটা যদি বার করি তাহলে আমরা দেখব CIK অ্যালগরিদম দিয়ে আমরা এই মেম্বারশিপ অফ এনি স্ট্রিংস আমরা বার করতে পারি ইন অর্ডার অফ W কিউবে বার করতে পারবো. সো দ্যাট ইজ দ্য থিং. আশা করি এতদূর পর্যন্ত যতদূর পড়ানো হলো বোঝা গেছে.